In today's tutorial, I'm going to teach how to calculate composite strength with the aid of AI. This tutorial is not only useful for those who work with composites in the lab but also helpful for those who use finite element software to predict the failure of composite structures. Engineering downloads. Hello friends, I'm Milad Shahsavari, and I'm here with an educational video on the design and analysis of composite structures using artificial intelligence algorithms. I'm a PhD student in mechanical engineering, specializing in solid mechanics, and my research focuses on the application of AI algorithms in mechanical engineering. I have over 18 years of experience working in various industries, and more than 15 years of teaching experience in Abacus software, collaborating with different institutions and universities. In addition to teaching basic and advanced Abacus courses, I've also conducted specialized workshops on the design and analysis of composite structures in Abacus, vibration analysis, and subroutine programming. So, as I mentioned, I've also conducted research and work in the field of AI applications within mechanical engineering. As I explained earlier, in this educational content, we aim to introduce the artificial intelligence algorithms that are used in the design and analysis of composite structures. And at the end, we'll solve a project related to this topic. This presentation is divided into several sections, and in the first part, we'll cover the basics of the subject. So, the use of composite structures and composite materials for various purposes is becoming increasingly common. For example, here we have a race car, or turbines, or different areas like the computer mouse we're using, or the body of an airplane, or even in biomechanics and mobile phone casings. They're also widely used in the medical field. Later on, we'll see some examples, like body prosthetics, or an artificial leg or hand, which are made using composite structures. And the more we look around, the more we see how extensively these structures are being used. To present this topic in a more scientific and referenced manner, I've included two charts here. In the chart on the left, we've shown the use of composite structures in the body of a commercial aircraft, where approximately 50% of the body is made from composites. The growth in the use of composites over the years up to 2010 is illustrated in this chart, and the reference for it is the article shown here. As mentioned earlier, our goal in this presentation is to ensure that every topic introduced is backed by references and scientific papers. In the chart on the right, the growth in the use of these structures in both military and civil aircraft is clearly visible, showing a sharp and significant increase starting from a certain year. This chart is extracted from a recent and up-to-date article that discusses the use of composite materials in the aerospace industry. So, we've reviewed how important these structures are across various industries, and here we've introduced a few examples with proper references. Design and analysis of composite structures, based on various references, which I'll introduce here, are generally divided into three categories: microscale, mesoscale, and macroscale. We can say that the output of each analysis level typically serves as the input for the next. At the microscale, we consider the properties of the fiber in the matrix as inputs. Parameters like VF, volume fraction, the distribution of fibers within the matrix, and the interface, meaning the connection between the fiber and the matrix, are all input variables. The output of this microscale analysis is the behavior of the layer formed by those inputs. At the mesoscale, we focus on the properties within each layer. For example, when carbon fiber is combined with a matrix like epoxy, with a specific VF, we analyze what properties emerge. This becomes the input for mesoscale analysis. Additionally, the layer stacking arrangement is also an input, such as how many layers we have and what fiber orientation each layer has. Once this analysis is complete, the laminate is evaluated to understand the behavior of the stacked composite. At the macro scale, we take a broader view. For instance, we analyze a structure with a thickness of 3 mm or 10 mm, and examine what overall properties it exhibits across that thickness, like the elastic modulus in direction 1 and direction 2. This structure is then analyzed as a whole. As I mentioned, various references have addressed this classification. For example, one reference includes the image shown here, and I'll introduce another reference as well. The reason I'm sharing these references is to help you cite properly if you ever need to write a report or document on these topics. Here's another reference that introduces the three categories and explains the analysis for each. This second reference is related to the chart shown here. Now, what are we trying to convey with this chart? Unlike homogeneous materials like aluminum, steel, or titanium, composite structures have directional properties, which introduce unique complexities. Each layer, depending on the fiber orientation, exhibits different properties compared to another angle. This directional nature of the layers makes the analysis of composite structures more complex than that of homogeneous materials. Classical and general analysis of composite structures typically falls into the four categories shown in this slide. The oldest method, and one that is still widely used, is experimental testing. Based on the building block pyramid, we can experimentally evaluate everything from the mechanical properties of input materials to the full composite structure. For example, we can determine the mechanical properties of a single CFRP layer, and so on. We can also assess the behavior of a composite structure under the loading conditions it experiences in its working environment. The second category is numerical methods, which usually involve commercial software like Abacus or ANSYS. The third method is based on existing relationships in composite structures, known as analytical methods. And finally, the fourth is using available references. For instance, if we need the properties of GFRP, we can refer to articles or books in that field. Each of these methods has its own advantages and limitations. For example, experimental testing can yield highly accurate results, especially considering manufacturing processes and potential defects. However, it requires time and financial resources, along with infrastructure either self-provided or through lab services. Numerical methods, as we all know, are prone to errors. These errors can stem from the engineer using the software, or from the inherent limitations of numerical solutions. But one major advantage is that there are no restrictions. We can evaluate any structure or geometry. Analytical methods are known for their precision. We use existing equations, substitute case study values, and obtain accurate results. However, as you know, analytical methods have many limitations. If our geometry is complex, we can say that analytical methods are almost unusable, and we're forced to turn to numerical solutions. In fact, numerical methods were developed largely due to the limitations of theoretical approaches. These are the pros and cons of the four methods that are still in use today, and many papers continue to be published using these approaches for composite structure analysis. Now, in recent years, artificial intelligence has been introduced to the world. Although AI has a much older history, its usage has significantly increased in recent times. It has entered the field of engineering as well, including the design and analysis of composite structures, which is the main topic of this educational content. So, we've introduced the four classical methods, and now we're going to explore the fifth method, using artificial intelligence algorithms for the design and analysis of composite structures. So, we talked about artificial intelligence. In this video, let's take a warm-up look at why the world has moved toward AI and what kind of help it has provided to human society. Here's a short example. It's just a few seconds long. Let's watch it together. This chart is quite fascinating. It highlights a very important point. The rate of fatalities in traffic accidents has been increasing. And when AI algorithms entered the engineering world, such as in the development of self-driving cars, they helped reduce the number of deaths caused by accidents. Image recognition is one of the subfields of artificial intelligence, which we can also refer to as computer vision. It's considered one of the most important branches of AI. Let's continue. As you saw, and I'll explain more in detail later, AI has entered various aspects of human life and has made significant contributions. For example, it can assist a visually impaired person in living a more comfortable and independent life. Now the video continues by introducing AI and explaining its subfields, which are mainly divided into two major categories: deep learning and machine learning. I'll talk more about these topics with you later. So let's move on with our slides and wrap up this part quickly so you don't get bored. So, as I mentioned earlier, and as explained in the video, artificial intelligence is divided into two categories: machine learning and deep learning. Let me also point out that this classification was introduced quite some time ago, and in newer books and references, it has evolved slightly. In the earlier classification, deep learning was considered entirely within machine learning. But in more recent frameworks, deep learning is partially a subfield of machine learning and partially overlaps with it. Now, we're not going to dive deep into this topic, because the goal of this content isn't to teach AI itself. I just wanted to give you a general idea and help you understand that these two subfields exist within artificial intelligence. Whether they overlap or not isn't really the focus of this educational content. If we want to briefly look at the history of artificial intelligence, there was a famous test called the Turing test, introduced in 1950. In this test, behind a partition, there was a human and a machine. A person, let's call them the interrogator, would ask questions, and both the human and the machine would respond. The interrogator had to determine whether the response was coming from a human or a machine. The machine responded so well that it became very difficult for the interrogator to distinguish between the two, because the machine's answers closely resembled those of a human. This moment could be considered the birth of artificial intelligence, when a machine was able to think and respond like a human. For example, there was a competition in 2011 called the IBM Challenge, where a host stood in the middle and various contestants participated in a Q&A format. IBM designed a machine that was one of the contestants in that competition, and the machine won. That machine had such a high level of general knowledge that it managed to outperform all its human rivals and win the contest. Or in 1972, during a chess match against a world-renowned chess player, a company organized a competition called Deep Blue. Deep Blue managed to defeat that skilled chess player. In fact, the machine was able to think through chess moves very effectively, predict future moves. Artificial intelligence isn't something that just emerged in the last 4 or 20 years. It has existed for a long time, but has gradually evolved into what we see today. To better understand the importance of addressing this topic, there's a journal called Technology and Innovation that is published annually. The section I'd like to introduce to you is from the 2021 edition of this journal. There's a very interesting table that categorizes and highlights the top performing fields across several domains. As you can see, some of the leading areas include 3D printing, robotics, big data, and AI. For example, the number of published articles, registered patents, the amount of investment in the field, and the market size across different AI sectors. This topic acts like a bright spotlight, revealing the significance of artificial intelligence and showing that professionals in the engineering field must inevitably enter this domain because it has become a professional necessity. My first presentation has come to an end. In this part, I aim to provide a clearer introduction to the topic and outline the overall direction of the work we intend to carry out. In the upcoming videos of this educational package, we'll delve deeper and more precisely into the main subject.